In this section, you will learn about implicit differentiation. First up, the difference between implicitly and explicitly defined equations. In an explicit equation, such as y equals 5x cubed minus natural log of x plus radical x, you can isolate the y variable. So we say that y is explicitly in terms of x. Whereas in an implicit equation, for example, x cubed minus 2y plus 3y squared equals 7x cubed minus the sine of y, you cannot isolate the y variable. There's nothing we could do to get the y by itself in this equation. So this equation is implicitly defined. Implicit differentiation is just an application of the chain rule. Remember, dy dx can be written as dy du times du dx, or you can think of it as the derivative with respect to x of f of g of x is f prime of g of x times g prime of x. In this example, find each derivative. First, we're going to do examples of explicit functions. Here, we have to find the derivative with respect to x of x cubed. And whenever the variable of the derivative and the variable of the function match, then that's going to be an explicitly defined function, and we find the derivative as we have been, in this case, using the power rule, and it would be 3x squared. Here, the derivative with respect to t of t cubed is also an example of a function that's explicitly defined in terms of t, because the variable of the derivative and the variable of the function exactly match. So then we can do explicit differentiation, and the derivative with respect to t of t cubed is just 3t squared. So when the variable of the derivative and the variable of the function match, as they did here with x and as they do here with t, that is an explicit function, and we do differentiation the regular way we've been doing it all semester. Now let's take a look at what happens when we have to do implicit differentiation. Here we have the derivative with respect to t of x cubed. So what you have to notice is that the variable of the derivative and the variable of the function don't match. And when that happens, we have to use implicit differentiation. To help you understand how it works, let's let y equal x cubed. Then the derivative with respect to t of x cubed could be written dy dt. And what you're going to discover is we can write that as dy dx times dx dt. And notice how this is exactly this form of the chain rule. So to find dy dx, that says take the derivative of x cubed with respect to x. Well, that's easy. It's just 3x squared. Then what we have to do is multiply that times the derivative of x with respect to t. Well, we don't know what that is, so we just have to write dx dt. So this is how we write the derivative. Similarly, here we have derivative with respect to x of y cubed. And once again, you just have to notice that the variable of the derivative and the variable of the function don't match. As soon as you see that, that's your signal that you're going to be doing implicit differentiation. So then here, since we already have the y variable and the x variable being used, let's let u equal y cubed. Then we can write the derivative with respect to x of y cubed as du dx. And using the chain rule, that can be written as du dy times dy dx. Now, because the u variable is explicitly in terms of y, we can find du dy. The derivative of y cubed with respect to y is just 3y squared. And then we just have to take that times the chain rule piece, which is dy dx in this case. And this is our derivative. So when the variable of the derivative and the variable of the function don't match, we have to use implicit differentiation. And really, that is just an application of the chain rule. We take the derivative of whatever variable the function is written in, and we do an explicit derivative with respect to that variable. So the derivative of y cubed with respect to y is 3y squared. And then we just multiply times the chain rule piece, in this case, dy dx. Now over here on this first one, we were trying to find the derivative with respect to t of x cubed. So what we did was think of the x cubed as the letter y, and then we could find the derivative of y with respect to x. So the derivative of x cubed with respect to x is just 3x squared, and then we have to just tack on the chain rule piece, which would be dx dt. And the chain rule piece is just the letter of the function. So in this case, it was x in the numerator, so dx in the numerator, and in the denominator will be the variable of the derivative, dt. Whereas over here, the chain rule piece is going to be dy in the numerator and dx in the denominator. In this example, we have to find the derivative with respect to x of the quantity x squared y to the fourth. So the first thing to notice is that we have a product here, so we will be using the product rule. That tells us to do f prime g plus f g prime, where the x squared will be the f and the y to the fourth will be g. So f prime will be the derivative with respect to x of x squared. Since the function variable matches the derivative variable, this is an explicit differentiation, and it's just 2x. Take that times g, which is y to the fourth. Bring down the plus sign. Then we have f, which is x squared, and we have to take that times g prime. Now for g prime, we have to do the derivative with respect to x of y to the fourth. So now the variable of the derivative does not match the variable of the function. So that means we have to do implicit differentiation. So first we take the derivative with respect to y, which would be 4y cubed. And then we have to multiply that times the chain rule piece. And remember, it will be dy in the numerator and dx in the denominator. Cleaning this up, we have 2x y to the fourth plus 4x squared y cubed dy dx. We can factor out a 2 and an x and a y to the third, and we would have left y plus 2x dy dx. And this is the derivative. Here we have to find dy dx given y to the fourth plus 3y squared plus 2y minus x squared minus x equals 5. There's no way to isolate the y variable and do an explicit derivative, so we're going to have to do implicit differentiation here. Now to get to dy dx, what we have to do is take the derivative with respect to x of both sides. So we will take the derivative with respect to x of y to the fourth plus 3y squared plus 2y minus x squared minus x, which then means we have to take the derivative with respect to x of the right-hand side, which is 5. Now notice that I didn't multiply by dy dx. That's not what we're doing. We are performing an operation on both sides, and the operation is the derivative with respect to x of the entire side. And the same on the right-hand side. Derivative with respect to x is an operator that's working on the right-hand side of 5. Now remember, anytime the variable of the derivative does not match the variable of the function that you're differentiating, we have to use implicit differentiation. So right away, when we want to find the derivative with respect to x of y to the fourth, that's going to be implicit differentiation, and it will equal 4y to the third dy dx. And again, that's because y is not x. Bring down this plus sign. When we take the derivative of 3y squared with respect to x, those also don't match, so that's implicit differentiation. We get 6y dy dx. Bring down this plus sign. Same thing here for 2y. The y does not match the x, so we find the derivative, which is 2, and then tack on the chain rule component of dy dx. Bring down this minus sign. Now when we take derivative with respect to x of x squared, that is an explicit differentiation, so that's going to be 2x, because the variable of the function is x and the variable of the derivative is x. Then we bring down this minus sign, and the derivative with respect to x of x is just 1. And for the same reason, it's an explicit derivative because the variable x matches the variable of the derivative. Now on the right-hand side, we are taking the derivative with respect to x of a constant. That's going to be 0. Now remember, our job was to find dy dx. So we're going to factor out a dy dx from these three terms here. Dy dx, and we would have to take that times 4y to the third plus 6y plus 2. Now this minus 2x and minus 1, let's throw over on the right-hand side. So that's going to become 2x plus 1. Now, to solve for dy dx, we need to divide both sides by this whole entire expression inside the brackets. So dy dx is going to equal 2x plus 1 over 4y cubed plus 6y plus 2. Now we see we can factor a 2 out of the denominator. So dy dx is going to equal 2x plus 1 over 2 times the quantity 2y cubed plus 3y plus 1. And this is solving for dy dx in factored form. Here we have to find dy dx given x cubed plus y cubed equals the square root of the quantity xy. To get to dy dx, we will need to take the derivative with respect to x of both sides. So on the left side, we have x to the third plus y to the third. And then on the right-hand side, we have to take the derivative with respect to x of the quantity radical xy. So I'm going to write that as the quantity xy to the 1/2 power. Now on the left-hand side, the first term is x cubed, and the derivative has a variable of x. So that means we can do an explicit derivative. So that will be 3x squared plus the y cubed does not match the variable of the derivative. So that will be an implicit derivative. So 3y squared dy dx equals. Now on the right-hand side, we have some stuff raised up to the 1/2 power. So we are going to be using the chain rule. So then that means the derivative is going to be 1/2 of the stuff, which is xy, decrease the exponent by 1, and 1/2 minus 1 is negative 1/2. And then the chain rule says we have to take it times the derivative of what's inside. But what's inside is a product. So we are also going to have to use the product rule. F prime g plus f g prime. So let's see what we get. F prime says take the derivative of the first thing, and the derivative with respect to x of x is 1. Take that times g, which is y, plus f, which is x, times g prime, which the derivative of y with respect to x would be 1 dy dx. So in order to apply the chain rule to find the derivative of what's inside, we had to use the product rule. And within the product rule, when we wanted to find g prime, we had to use implicit differentiation. So then let's clean this up. On the left-hand side, we have 3x squared plus 3y squared dy dx equals, on the right-hand side, we can write this as a rational expression. The 2 and the radical xy will have to head to the denominator. And the y plus x dy dx stays in the numerator. Now ultimately, remember that we have to solve for dy dx. We have one here, and we have one here. So we need to do some algebra now. So first what we'll do is just multiply both sides by 2 radical xy. So if we bring that to the left-hand side, it will multiply 3x squared plus 3y squared dy dx. And on the right-hand side, it will just go away, so we have y plus x dy dx. Let's go ahead and distribute. So 2 times 3, now we have 6, and then we have x squared times radical xy plus, we take the 2 radical xy times the second term here, and we get 6y squared radical xy times dy dx. Equals, nothing changes on the right-hand side, y plus x dy dx. So now what we want to do is keep any term that has a dy dx in it on the same side. So we'll keep this one on the left side, and we'll need to move this one by subtracting it over to the left side. So then we have 6y squared radical xy dy dx minus x dy dx equals, now this y is going to stay on the right-hand side, and we will want to subtract over the 6x squared radical xy. So now let's factor out this dy dx. And we would have 6y squared radical xy minus x. On the right-hand side, we still have the y minus 6x squared radical xy. Now to isolate the dy dx, we need to divide both sides by this expression. So we will have dy dx is equal to, we put this right-hand side in the numerator, y minus 6x squared radical xy over 6y squared radical xy minus x in the denominator. Now, something that happens a lot in implicit differentiation is we can make a substitution. Remember that we were given x cubed plus y cubed is equal to the square root of xy. So everywhere we see the square root of xy, we can replace it with an x cubed plus y cubed and thus get rid of the radical. So the square root of xy is going to get replaced with x cubed plus y cubed. So then this is going to become, in the numerator, y minus 6x squared times the quantity x cubed plus y cubed over the denominator, which is going to become 6y squared times the quantity x cubed plus y cubed minus x. Now, if we simplify this, in the numerator, we will get y minus, now we have to distribute the 6x squared times the x cubed to get 6x to the fifth, and then we have to distribute, don't forget the minus sign, 6x squared times the y cubed, so we have minus 6x squared y cubed over, distributing in the denominator, we will get 6x cubed y squared plus 6y to the fifth minus x. And this is dy dx in simplest form. In this example, find the equation of the tangent line at the point 13, 0. We are given the equation x plus xy squared plus sine of y equals 13. Now, to find the equation of any line, we need two things: a point, which we already have, and a slope. And we know that the slope of the tangent line is going to come from the derivative. Since this is an implicitly defined equation, we will call the derivative dy dx, and we will have to evaluate that at the point 13, 0. We don't call it f prime of x because there's no way to isolate the y and say y equals f of x. That's why we call the derivative dy dx here. So to get to dy dx, we need to take the derivative with respect to x of both sides. So we will have the derivative with respect to x of x plus xy squared plus sine of y, which means we have to take the derivative with respect to x of the right-hand side, which is 13. So derivative with respect to x of x, that's an easy one, it's 1. Then derivative with respect to x of xy squared, we have to be careful here. Since this is a product, we are going to have to use the product rule on this one. So we will be doing f prime g plus f g prime. So let's bring down this plus sign. Then the derivative of the first is the derivative of x, which is 1, times g, which is y squared, plus f, which is x, times g prime. Now because y is not x, we have to use implicit differentiation on this one, and we get 2y dy dx. So now this one is done, and now we have to find the derivative with respect to x of sine of y. Because y is not x, once again, we have to use implicit differentiation. And the derivative of sine of y will be cosine of y times dy dx equals the derivative with respect to x of the right-hand side, which is 0. So let's clean this up a little bit. We've got 1 plus y squared plus 2xy dy dx plus cosine of y times dy dx is equal to 0. So now any terms that have a dy dx, which is these two, we're going to keep on the left-hand side, and any terms that don't, which is the 1 plus y squared, we will want to move over to the right-hand side. So we will start with these two and factor out the dy dx, and we will have 2xy plus cosine of y, and then we will subtract over the 1 and the y squared to the right-hand side. So we have negative 1 minus y squared over there. Now we can solve this for dy dx, and that's going to equal negative 1 minus y squared over 2xy plus cosine of y. And now this gives us the value of dy dx everywhere on the curve. Remember, what we are interested in is the slope of the tangent. So that means we will need to find dy dx evaluated at the point 13, 0. So to find the slope of our tangent line, we will need to evaluate dy dx at the point of the tangency, which is 13, 0. So now we just plug this in. In the numerator, we will have negative 1 minus y squared, and the y value is 0, over, in the denominator, we have to take 2 times x, which is 13, times y, which is 0, plus the cosine of y, so cosine of 0. Now this is going to equal negative 1 in the numerator, and in the denominator, we have 0 plus cosine of 0, which we know is 1, so our slope is negative 1. Now remember, we have our point, which is 13, 0, and now we have our slope is negative 1, so now we can plug into point-slope form, which is y minus y1 is equal to m times x minus x1. And when we do that, we have y minus 0 is equal to negative 1 times x minus 13. Simplifying that, we get y is equal to negative x plus 13. And this is the equation of the tangent line at the point 13, 0. Here we have to find d squared y over dx squared, which is the second derivative for x squared plus y squared equals 49. Now, to get to the second derivative, we first have to find the first derivative. So we will take d by dx of the left-hand side, x squared plus y squared, which means we have to take d by dx of the right-hand side, 49. Derivative with respect to x of x squared is 2x plus derivative with respect to x of y squared means we have to use implicit differentiation, so that will be 2y dy dx. On the right-hand side, the derivative of a constant is 0. We see that we can divide through everything by 2, and now we will have x plus y dy dx is equal to 0. So now we will want to isolate the dy dx. So let's subtract this x over to the right side, and we have y dy dx is equal to negative x, and then we just have to divide both sides by y. So we have dy dx is equal to negative x over y. And this is the first derivative. Now, in order to find the second derivative, d squared y over dx squared, we will need to take the derivative with respect to x of the first derivative. So if we do this to the left-hand side, then we will need to do the same thing to the right-hand side. D by dx of negative x over y. So to find this derivative, we can see that we will need the quotient rule, which is f prime g minus f g prime over g squared. So let's go ahead and take this negative sign out front. And now we will apply the quotient rule to x over y. F prime is the derivative of x, so that's going to be 1 times g, which is y, minus f, which is x, times g prime. Now, to find the derivative of y with respect to x, we have to use implicit differentiation. So that will be 1 dy dx. Now that whole thing has to be over g squared, so that's y squared. So now let's simplify. We bring down that negative sign. Let's go ahead and get our fraction bar. This first term is y. We bring down this subtraction, and then we have x times dy dx. And in the denominator, we have y squared. Now remember, we already solved for dy dx, and we found out that it is negative x over y. So then we can make this substitution here. Bring down the negative sign. We have y minus x times the quantity negative x over y over y squared in the denominator. Then this is going to equal negative. In the numerator, we have this y, and this is going to turn into plus x squared over y, that whole thing over y squared. Now, to clear this complex fraction, we want to multiply by 1 in the form of y over y. So then this is going to equal negative. In the numerator, we will have y squared plus x squared over, in the denominator, we will have y cubed. But now remember, way back at the beginning, we know that x squared plus y squared is equal to 49. So we can make that substitution, and this becomes negative 49 over y cubed. And this is d squared y over dx squared, which is the second derivative.